Okay, can you hear me? Yes? Okay, so yeah, let's get started. So hello everyone, this is SeungryongKim. So today we will continue the 3D computer vision. So last week we discussed so many kinds of concepts in 3D computer vision. One was the we discussed the kinds of 3D representation, and we discussed how to reconstruct 3D model by multi-view geometry or the monocular depths, or we also discussed the unsupervised learning for the 3D reconstruction field, right? So yeah, it was like this. So today we will move to the more advanced concept, neural latency field, or the implicit neural representation. So to discuss this one, we have to start from the overview synthesis. What's an overview synthesis? There are three kinds of overview synthesis. The first one is view interpolation problem, which aims to render view that are similar or between photo views. For example, let's suppose that we have a scene like this. Now let's suppose that we take a pictures here and here. In this case, we have two images, right? And view interpolation means we want to generate new images that are similar or between two photos or the given images. So this is called the view interpolation. Similarly, view extrapolation aims to render the view from the arbitrary position or the orientation. For example, not between photos, but also we want to generate the images like this from these given images. This is the view extrapolation problem. So of course, this problem is going to be the much challenge than the view interpolation problem. Another kind of problem is the view manipulation, which aims to change the material, lighting, or the content of the image or the scene. So this is three kinds of the novel view synthesis problem. So in computer vision area or computer vision field, this novel view synthesis problem was the has been popularly used during maybe 30 decade. Previously, when the deep learning revolution started, there was the first paradigm. Neural network is the black box that directly render the pixel. So in first paradigm, I mean early paradigm, neural rendering was formulated by formulating this neural network take up input and output image directly. But new paradigm occurs. Paradigm A. New paradigm is like that. Neural network is just a black box that model the geometry of the world, not a pixel or not an image directly, just a model the geometry of the world, and then non-learned graphics engine render it. So in this paradigm, we just use the neural network to represent the scene, not images, and render the images from the scene by using the non-learnable graphics engine, because this graphics engine has been studied in many graphics applications. So we just use this one, and then we just use the power of the neural network to model the geometry of the world. This is a new paradigm. So this is the implicit representation, and this is so-called the scene representation. NeRF is one of them. Okay, so this is a neural rendering paradigm. Then how can I use this neural rendering paradigm to solve the view interpolation problem? So view interpolation problem is like that. So input the sparsely sampled images of the scene, and output is the new views of the same scene. I mean the view interpolation or the view extrapolation. We can just call this kind of task as a view synthesis. let me show you examples here. Question. This is the kind of the view synthesis. This video, this multi-view video generated by null, given a few fixed view images. This is another example here. As you can see here, the novel view are plausibly generated by the neural network. As you can see here, right? This is another examples. This one, okay? Yeah, this is novel problem. So, in early novel view synthesis field, there was were used as a continuous safe representation. So this is called the occupancy network. What they do, what the authors do in this paper is that they want to represent the this 3D field as a occupancy field. So like this. So let's think this 3D field in a 2D space like this. And let's suppose that there is the object boundary, and we can give values to the each pixels. I mean each position. Let's suppose that x, y, g. Then if x, y, g is inside of the outside of the object, it should be negative. Or if the x, y, g is inside the object, it should be positive. Then we can model this one as a mapping function from the P. P was the how to say the coordinate, right? Coordinate to the occupancy value. Occupancy value. Which this mapping function is modeled by the neural network with parameter setup. So then you can represent your neural net, your space implicitly looks like this. This is the occupancy network in CVPR 2019. Similarly, there was many attempts to represent the neural to represent your 3D field by by using the neural network as a continuous shape representation. First one is the occupancy network, as we discussed in previous slide, XY. So in this paper, we will learn the mapping function from the coordinate to the occupancy field. Similarly, there was a deep SDF in CVPR, not CVPR, ICCV 2019. CVPR. Let me check here. Let me check this one later. Anyway, there was a deep SDF. In this model, we want to learn the mapping function from the XYG to the distance. The distance is similar to the concept. The distance concept is similar to the occupancy concept. Occupancy is just occupancy, but distance can be modeled by the distance from this implicit object boundary or surface boundary. So SDF is larger than or greater than 0 if the this XYG is outside of the surface boundary, and SDF is negative if the point is inside the surface. And after that, there was a similar work, scene representation network. In this paper, they want to learn the mapping function from the XYG to the latent vector. In this case, they want to learn not a distance only, but also they want to learn both color and distance to generate the colored point cloud like this. Similarly, in 2020, there was a differentiable volume rendering technique where they just learned the mapping function from the coordinate to the color and occupancy field, and they just generate the images by using this color and occupancy in 3D point cloud. So it was the only method, and yeah, the purpose was like that. So here was the input image, and by using this implicit mapping, implicit representation, this occupancy network can generate the occupancy field here from the single input image. So this network just run the mapping function from coordinate and conditional input to the output, like this 3D field. It was an occupancy network, but it has a limited rendering model. It has a limited rendering performance, so it is difficult to optimize, even though it has the highly compressive capability. So to overcome the limitation of this previous impulse representation method, there was a NERF, neural radius field, in ECCB 2020. This paper, by the way, got a best honorable mention award in ECCB. And after this NERF paper, everything's changed in 3D computer vision. It means that inference representation is going to be pervasive based on this NERF space, NERF technique. In fact, this NERF paper is just the extension of this previous method, scene representation network, or the differentiable volume rendering. But in NERF paper, they showed, the authors showed that we can generate high quality and high resolution images using this impulse representation. This is NERF. So, what is NERF? What is NERF? NERF aims to synthesize the null review of the complex scene by optimizing an underlying continuous volume scene function using the sparse set of the input view. Again, synthesizing null review of the complex scene by optimizing the underlying continuous volumetric scene function using sparse set of the input view. So first of all, we want to model 3D field, right? In general, 3D field is the continuous volumetric scene, right? Continuous volumetric scene. So to represent this one explicitly, maybe it's going, maybe the very challenge. So there was the approximated way to represent this continuous volume space in previous methods. For example, point cloud or the box representation or something like this. But in this paper, in NERF space, we can model this continuous space as a neural network. Neural network, because this neural network has the very, very good capacity to represent this continuous volume scene. So in this paper, we cast this problem as a continuous volumetric scene function modeling. So how can I do that? So first of all, we are going to take input as input position and direction. Position is just the coordinate x, y, z, and direction can be determined by two parameters, theta and pi. This is just the camera viewpoint, like this, right? And then f theta, neural network generate RGB and density. Density is similar to the occupancy in previous method, density. So this point can have color and density. Similarly, by taking every point or the viewpoint as a possible query for this neural network, we can generate sparse color and density field. Then by using the volume rendering function, this is just a non-nullable rendering function, we can render the color value, in this case the one color value. And because we already know the ground truth at this point, because in this case we just suppose that we have a two view images, right? Two view images with known camera pose. Then we can say that we have a GT images or GT cover value, and by just minimizing this loss function, we can backpropagate loss gradient to this neural network, and finally we can achieve this neural network which have the capability or the ability to generate this scene in a continuous and manner. Yeah, this is the neural radiance field. Let me show you one video, very short video that describes the nerve generation process. Sorry. Okay, this is just a video.
Given a set,
please let me know if you are not hearing about the audio.
Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene
여러분
as
오디오
a
혹시
vector-valued
들리나요?
function,
들리나?
which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize the scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding.
다시 해봅시다. 이거 짧아 한 3분 정도 되니까 설명을 사실 제가 하는 것보다 요 너프 원저자분이 올려주셨던 동영상이 너무 잘 만들어서 이걸 좀 볼게요.
Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we are able to optimize the scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. We first show comparisons to top-performing methods on synthetically rendered data. Scene representation networks implicitly represent a scene using a fully connected neural network. SRNs have issues with multi-view consistency and are unable to represent high-frequency details. Local light field fusion uses a pre-trained network to promote each input view to a high-resolution 3D volume. Inconsistencies between adjacent volumes causes flickering artifacts. Neural volumes encode a scene as a 128 cubed voxel grid and use a warp field to better allocate these limited samples. However, they're still unable to represent high-resolution content, such as the fine details in the ship's texture and rigging. We see the same trend in all of our synthetic test scenes. Our method both qualitatively and quantitatively outperforms the other methods. Here we show the results of our method on the 6 other objects in our realistically rendered dataset with complex geometry and non-Lambertian materials. Next we will show comparisons on real scenes, captured with a forward-facing phone camera. SRN uses a recurrent network to ray march through encoded scenes, resulting in an inconsistent appearance between rendered views. LLFF blends between multiple renderings with different limited fields of view, resulting in flickering artifacts along image borders. Here, only our method can represent fine details with complex occlusion effects, such as the ribs in this fossilized T-Rex skeleton. Now let's take a look at some additional real results. We can visualize the view-dependent effects captured by our representation, such as the semi-transparent appearance of the olive oil bottle and specularies on the stove, reflections on this room's television and specularities on the conference table, and sharp reflections and speculations.
들리시죠? 아이고, 네. 아이고, 미안. 네, 여러분들 이거 보여준다고 하다가 오디오가 꼬였네요. 미안해요. So anyway, the core of the nerve is just a neural network, etc., which take a special position x, y, z, and viewing direction theta and pi, and RGB output, RGB color value, and output density. So in general, it consists of the 9-layer with 256 channel, but it depends on your it depends on your images. And yeah, so this is just a network to render your scene. So even though this network can represent your scene in infinitely many points, it may be possible to query the every possible point in the 3D field. So in this case, we have to just sample the point. Then how can we define? How can we decide the samples? So if we have the camera pose here, we just define the lay. You just define the lay from the by O. O means the camera center, and T is the direction, and T is just parameter. And we can consider this lay. Then from here we just sample the point, sparsely sample the point, query point. Then for each query point, let's say this is the TI or the small ti. By using the neural network, we just sample the CI and density sigma I. Then by finding CI sigma I for every sampled point, then aggregate these values, we can determine the color value for each lay in this viewpoint. So how can I do that? We just aggregate the n kinds of the values, large Ti times alpha I times Ci. In this case, Ci is just the colors that are coming from the neural network. In this case, Ti is just a weight which represents how much light is blocked only or only. So this one is just computed by multiplying 1 minus alpha j. From j is from 1 to the I minus 1. Alpha I is just represent how much light is contributed by lay segment I. And delta Ti is just like delta T is just like this distance, and sigma I is just network parameter, network output density, that's network output, and 1 minus exponential to the negative sigma I times delta Ti. This is just alpha I, and by just multiplying Ti, alpha I, and Ci, and aggregating all of the output, we can just achieve the C, 1 pixel value in these images, right? And by considering whole the point on the whole possible lay and whole possible sampled point, we can generate the images in this view. Then during training, we can train the networks by minimizing the rendered images and GT images distance, like this. And testing time, we can render the arbitrary view images by just using the feed-forward network. This is a volume rendering part in the nerve. Then how to optimize your networks, your network parameter theta. As we discussed so far, we just model the rendering process by render f theta. I means ice view, ice view. images, and etc. is our network. And by considering the whole process of the rendering, we can just minimize the distance between the ground truth or the given view images and rendered view images, and just finding a setup that minimizes the distance loss function. This is just a test time optimization. So given a view, multiple view at test time, you're just to minimize this loss function and optimize your network with gradient descent and just generate the novel view. This is the NERD in training time. And again, to train the network to reproduce whole input view of the scene, whole input view of the scene. So let's suppose we have so many kinds of novel given view. Let's say 100 or 200 images or 200 view images by training the network, single network that satisfy whole these given images like this loss function. We're gonna have the neural network etc. that can represent this scene in a continuous and continuous manner. So this is a NERD. Question. 자, 설명 좀 빨리 왔는데 질문. Question. 다음 질문이 잠시만요. 프로브 월 마이너스 알파 제가 이거죠 이거 알파 플러스 제가 가트가 프로브 이거 아날로지컬 리전 여기 말 그대로예요. 무슨 얘기냐면은 한국말 설명할게요. 이게 결국에 이 시기 하고 싶은 거는 보면은 결국에 우리가 3D 필드 표현한다고 하는 거는 이 3D 필드 안에 어떤 오브젝트가 이렇게 존재를 할 거잖아요. 그쵸? 3D 필드에 오브젝트가 존재를 할 건데 이 TI가 그러니까 TI가 매저하고 싶은 거는 how much light is reflected. 그러니까 우리가 빛을, 그러니까 레이라고 하는 걸 결국에 이 뷰에서 빛을 썼다 생각할 수 있는데 여기가 쭉 오면서 오브젝트에 막힐 때, 그쵸? 오브젝트가 얼마큼, 그러니까 오브젝트가 있으면 빛이 막히겠죠? 만약에 오브젝트가 없었으면 이 빛이 계속 날아갈 텐데, 그쵸? 얼마큼 빛이 막혔느냐를 매저하고 싶은 거예요. 그쵸? 얼마큼 빛이 막혔느냐 매저하고 싶은 거 결국에 빛이 막혔을 때 여기 오브젝트 있다고 가정할 수 있으니까 오브젝트 바운더리가, 그쵸? 근데 그거는 사실 뭐로 측정이 될 수 있냐면은 이 현재까지 이 i번째 포인트까지 오기 이전에 있었던 애들의 이거 뭐랄까요? 요 알파 i의 영향을 받는데 알파라는 게 도대체 뭐냐? How much light가 contribute? 그러니까 이 레이 세그먼트 이 레이 중간에 그러니까 결국 이 레이 하나를 우리가 모두 표현할 수 없지만 샘플링을 한다고 했는데 이 두 개의 샘플 사이에 요 빛이 그쵸? 이 알파가 이 density 뭐예요? 이 시그마 i를 통해서 요 결정되는 이 알파 i가 결국에 빛이 얼마나 요 레이 위에 포함되어 있는가를 나타내는 게 이 알파 i니까 그 알파 i를 1 마이너스 설명해줬네요. 네, 1 마이너스 알파로 바꿔서 서메이션 해주면 여기까지의 빛이 얼마나 와 있었는가, 그러니까 빛이 얼마나 있었는지를 표현하는 거고 간단히 생각하면 이게 오브젝트가 없었으면 그냥 다 거의 0이겠죠. 그렇죠? 왜냐면 시그마가 다 0이었을 테니까. 그렇죠? 맞나? 맞죠? 시그마가 다 0이었을 테니까 얘가 알파가 0이고 그 1이죠. 1. 그렇죠? 쭉 그 1만큼 곱해지는 건데 알파가 시그마가 커지면 작아지겠죠. 맞죠? 그렇죠? 그러니까 빛이 더 블락티 많이 됐으니까 그렇게 해주시면 되고 제가 봤을 때 말처럼 결국에 이게 사실 이 논문에 처음 제안한 게 아니고 원래 그래픽스에서 아까 앞에 제가 설명했던 것처럼 디퍼런셔블 렌더링 여기 이 렌더링 엔진, 그래픽스에 많이 쓰는 렌더링 엔진에서 쓰는 개념을 갖고 온 거고요. 알파 컴퓨션과 사실 거의 똑같은 개념이죠. 맞아요. 자, 영은 학생 질문이 혹시 제가 좀 설명이 부족하면 아마 저보다 이거 잘하는 친구들이 많이 있을 것 같은데 이 방에 좀 같이 설명해 줘도 돼요? 영은 학생 질문이 덴시티. 자, 덴시티는 말 그대로 덴시티예요. 그러니까 이 3차원 필드가 쭉쭉쭉쭉쭉 레이를 쏴서 이 점이 있었다고 줬을 때 이 XY 점에서 XYT 점에서 칼라 값, RGB 값과 칼라 값을 알 수 있는데 여기가 진짜 그 아큐판시 즉 오브젝트니스인가 그 오브젝트가 있을 프로버빌티라고 보면 되죠. 덴시티. 그렇죠? 그리고 이건 그냥 사실 단순히 그때의 칼라 값만 나타나 있는 거고요. 다시 얘기하면 저 칼라 값 자체가 그 덴시티를 표현할 수가 없기 때문에 이렇게 칼라와 덴시티를 나눴다고 보면 될 것 같아요. 알겠죠? 그러니까 조금 쉽게 설명하면 요거랑 똑같아요. 요 아큐펀시. 요 아큐펀시라는 개념이 결국에 널프에서 덴시티라고 볼 수 있을 거고요. 어차피 저거는 우리가 GT를 주는 게 아니라 저 필드 자체를 그 이미지로 렌더링해서 이미지 러스를 흘려주기 때문에 그러한 특성을 갖도록 그냥 모델링 했을 뿐인 거죠. 익스프레션에 넣어주는 게 아니라. 네. 칼라가 진할수록 네, 그러니까 그게 좀 달라요. 그러니까 칼라가 진할수록 덴시티를 표현한 게 아니라 여기서 그냥 칼라는 그냥 오브젝트의 칼라만을 표현하도록 모델링을 한 거죠. 그러니까 어떻게 보면 디컴포즈를 해버리는 거죠. 네트워크가 배워야 되는 걸. 칼라는 정말 칼라만 모델링 하도록 한 거죠. 됐죠? 왜 그렇게 되느냐? 우리가 렌더링 식을 이렇게 뒤에서 정의를 내렸기 때문에. 그렇죠? 렌더링 파트에도 이렇게 정의를 내렸기 때문에 저 칼라는 덴시티가 아닌 그냥 칼라 값 자체만 포함하도록 설계가 된 거죠. 알겠죠? Question. No? Okay. Let me continue. Even though these neural networks can represent infinitely many possible points, it's going to be the how to say impossible, that's right? Impossible to query every point. So we have to sample the point, sample the point in a ley line, right? But it has a trade-off, right? So the best model is going to be the whole infinitely possible point in the lay to render these color images. But if we sparsely sample the point in the lay, we may lose some quality, even though we can reduce the complexity, right? So it has a trade-off. So to overcome this trade-off, in this original paper, they proposed the two-path rendering technique. So how can they do that? They have a coarse page and fine page. In coarse page, they have one neural network. First of all, they just sample sparsely and regularly, like this. Then just render the images and train the network. But in this case, we can think this one, Ti times alpha I as a weight or the probability distribution for the new samples. Let me say like this. Then, based on these values, we can just assume that we are interested in this region rather than this region. I mean, we are not interested in the background or the inside object. We are just interested in the object boundary, 3D boundary or 3D surface. So based on this coarse probability, we more densely samples in the fine phase and then train another network to generate fine grain image generation. So this is a two-path rendering technique. And this is in detail detailed architecture for the NERD. So input was the position and direction, right? Interestingly, they did not use position and direction directly. They just to give position as a very early input, and they just use the direction in the almost the end of the networks. First of all, they just take input position and extract the picture vector and use the input position again in here. This act like a circuit connection and encode the picture vector and generate the density for this input position. Interestingly, this density is the pure agnostic. So in this case, we don't need to use the direction to generate the density, but in NERV model, they just model color should be view dependent, right? In other words, if we change the view, the color should be changed accordingly. So they just add color value at here and generate the pixel color value here. So this is just the MLP based network structure for the NERV. Why do we have to view depend on the color? So you can understand this here. So this is the one view images and this is other view images. Let's suppose that we are interested in the same 3D point here and here, here and here, and here and here. Even though there are same color, same 3D point, when we project this 3D point to the when we project the different view images, it has different color value due to the many regions, for example, like the shadow or the reflectance or illumination condition, so on, right? So in here, when you considering the color value at the same point by varying the view direction, the color will be changes as change the view. I mean according the view direction. So based on to account for this kind of tag in NERD, they model view dependent color prediction by using this kind of neural network. Right. So one more thing is that our position was just x, y, z, and view direction theta, pi. So which is just like 5 by 1 vector. So this is just a very low frequency input. So which may generate the limited query images. So in this paper, they also proposed to use the position embedding technique to increase the frequency of the input values. So by using this kind of the predefined sinusoidal function, this is exactly similar or same to the position embedding in transformer. We can just improve the frequency of the input data, so the network can easily learn the mapping function from this high frequency input to the color or density values. So this is a position embedding. That's why the input of the neural network was the high dimensional 60 by 1 or the 24 by 1. This is a position embedding. So this is the comparison, an overview synthesis performance comparison of the NERV with SRN previous implicit representation by considering by generating color and view dependent color and view agnostic density with the neural network NERD can generate the high quality images even at noble view. This is one images, and this is another images. Let me show you another examples. Understand? Yeah, this is the rendered view. This is synthetic data, and where's the rendering performance? Yeah, here. So because we have a learned model during the training, at testing time we can generate or we can manipulate your scene in a 3D aware manner by changing viewing direction or just view dependent appearance here. Yeah, this is another example. This is a rendered view, and this is a fixed view with different color deformation, view dependent color deformation. Like this. 멈췄네요. Yeah, listener. Interestingly, because this density is related to the occupancy of the input scene by just render this density only without considering the color value. You can just generate the depth map, interestingly, here. So even though we did not use any kinds of the depth map during training, we just considered the color value during training. But at test time, we can generate detailed geometry or the occlusion. Looks like this. And interestingly, because we have a geometry value, you can just generate explicit mesh model by using the handcraft merging cube algorithm on the implicit field. Let me give you examples. Yeah, this is generated depth map. The quality of the depth map is impressive, right? This is depth, and yeah, this is the mesh model generated by merging cube. We can adjust or we can manipulate viewpoint or the camera folds like this. So this is rendered explicit math model. Overview. Can you hear me? No? Okay, yes. Thank you. Okay, so yeah, let's continue. Yeah, it was nerve. By the way, we will have a final exam on June 15 from 2 to the 4:30 p.m. 그쵸? And after 2 weeks, so it's going to be offline, similar to the midterm exam, and the location will be announced soon. So please remember. Question about final exam. The problem style will be similar to our midterm exam. Okay. 16. Let me check. 16. 16th. Same time. After 2 weeks. Okay. Right. So it was nerve. 시험범위 아직 안 정해졌는데 일단 수업 시간에 배운 건 전부 다 커버하는데 지금 중간고사 범위를 포함할지 안 할지만 정하면 될 것 같은데요. 네. 그것도 정해지면 알려줄게요. 일단 우리 오늘 3D 초 끝나고 다음 주까지 마지막 1시간 하는 범위까지가 포함이 될 거예요. 근데 처음부터일지 중간고사 이후일지만 제가 정해서 알려줄게요. 그렇죠? Right. So, it was snoring. We already have class on Thursday but final. It should be Thursday. Final exam will be on Thursday, right? 16th. 맞는데? 16th. Thursday. Yeah, Thursday is 16th. Okay. Yes, right. Okay. Right. Let's move to the pixel lab. So nerve. Original nerve was the unconditional version of the neural network. I mean, so it is inherently test time optimization. So given a few images, I mean a few view images, not few images, multi-view images, original nerve was optimized during the test time, right? So this is just called test time optimization. But in pixel nerve, the authors tried to formulate the nerve as a conditional version. So this is called conditional nerve. In other words, they want to formulate nerve to generate the novel view from the one or few images as an input. So this is just called few shot neural radius field. 노블 뷰 synthesis, 노블 뷰 MVS로 합시다. 퓨전 MVS. So like this. If we just have a 3-view input for the complex scene, this pixel lab can generate the novel view, while original nerve is a nerve frequently fail to generate the plausible output given a very few images, for example 3-view or the 1-view. So this is pixel lab. So how can we formulate this one? The main idea of the pixel nerve is that predict continuous neural scene representation conditioned on one or few input images. In other words, okay, so in original nerve, the neural network just take a x coordinate, let's say just XYG coordinate and viewing direction, theta and pi, and generate RGB and sigma. But in conditional, they additionally use feature vector, given the input condition images. How they formulate this? First of all, let's suppose that we have an input view, original input view. Let's say we just consider the view. Then we extract the CNN feature vector. CNN feature vector is going to be the here h by w by c. C, let's say this is a w, tensor w. Then we are interested in this pixel, xy and xyg and theta and pi here. Then because we already know camera port difference between input view and target view, we can consider the corresponding feature vector from the input view by considering the projection of this 3D point, let's say vector x to this point, image point. So it's going to be pi x. Then we can use this feature vector as additional input for the neural network, where we want to network, where we want to make a network be more aware of input images, because this is input feature, right? Then this network can generate the better RGB sigma with more information, with input conditional information. By formulating original nerve like this, we can train scene prior, because during training we have so many kinds of images, other scene images. So during training, we can train the network, can be aware of the scene prior, so then it enables us to solve the few shot no review synthesis. So this is pixel nerve. Of course, the rendering procedure or the loss function is exactly the same, but this is not a test time training. This is just a training phase, a training based method on the multiple scenes to run a scene prior. By using this, we can just generate no review even for few shot input data. This is just a single view case, one shot case. If we have a multi-shot, let's say 3-shot, then we can just extend this one to consider input multi-view. How? Because this feature vector can be extracted from the every view, right? And we can just aggregate this feature vector to generate a better output, no review input, no review images. So this is just a network architecture. So comparing to the original nerve, it has the additional branch to give feature vector as an additional input like this. Then this is just used to generate the RGB and density value. And if we have the n input, let's say n is very, very small, n is equal to 1 or n is equal to 3 or to 5, then we can just average this, or we can just aggregate intermediate feature vector and finally generate the RGB and set RGB and density. This is a pixel nerve architecture. Yeah, this is output. Given the 3 views of the handheld scene or the complex scene, this pixel nerve can generate the plausible or high quality novel view, while nerve fails to generate the scene, thanks to the conditional formulation and the learning the scene prior from the training data. This is a pixel nerve. We will see more detail in the start presentation. Anyway, there was another direction, generative neural network field. Generative neural or the generative neural network field. We discussed this one in the 3D GAN, 그렇죠? We discussed this one, generative neural network. There was the one research direction, 3D aware image generation, right? 3D aware image generation. Sorry. To make our network 3D 3D aware, previous method just consider the explicit 3D representation, voxel representation, or the 3D picture representation, which was a hologram. But in here, giraffe, we just consider the neural network field to generate 3D aware image generation. So this is the graph. So this is the detailed architecture of the graph. Oh, by the way, question. If we use the prior knowledge, is the convergence time to train the pixel up shorter than NeRF? Yes, exactly. So in original pixel art, the author shows that this pixel art can generate by just the one bit port or optimize or fine-tune given specific scene. But in that case, the convergence time is going to be much faster than the original NeRF that are starting from the scratch, 그렇죠? Random scratch. Yeah, this is graph. The network architecture of the graph is the interesting. Let's say G theta. In this case, lay sampling and the point sampling is similar to the previous NeRF or the pixel NeRF. So we just have the lay and 3D point. But in this case, this graph take additional two more vectors, shape code vectors and appearance code vector, GS and GA. And we just assume GS and GA have independent phenomena, and these two kinds of code act like a shape code and appearance code. And just to give these two vectors to the NLP G theta, then we generate CR and sigma R. And we use the same volume rendering to generate the CR. This is a comma value, and predict the patches. Because this is the very large scale network, so we cannot generate the image directly. So in this paper, they just consider the patch generation. Anyway, so generate the patches. We do not have the ground truth, right? This is because this is a generative model, so we do not have the ground truth similar to the GAN. So we use the discriminator to train this network. So by using the real patch, we use the discriminator. We train this neural network that can generate realistic images while following shape code and appearance code. They are sampled from the random noise. At testing time, by just randomly sample shape code and appearance code, we can generate any kinds of images in a 3D aware manner. Yeah, 3D aware manner. So this is output of this graph. So what can we do further in this kind of technique? First of all, we can do camera pose interpolation. For example, so okay, let's suppose that we have a trained random network here. Now, if we fix shape and appearance code and just to move camera direction, camera parameter K, then we can generate the multi-view images in a 3D aware manner. So comparing to the hologram, 2D explicit 3D representation based method. This implicit 3D representation based method graph can generate the more high quality images. This is the graph, and by extending this one to the multi-instance object, there was the giraffe. The giraffe paper got a best paper award at UPR last year. Idea is very similar to this graph. This giraffe paper incorporate compositional 3D scene structure into a generative model. So far we just considered the one single model. So we just assume that given a scene, there is only single object or single instance. So yeah, so this is like this. But in giraffe paper, in general images, they often have a multiple instance, right? So in giraffe paper, they formulate multiple independent neural networks field and just composite them and generate images from this compositional 3D scene structures. So this is the giraffe paper, and by randomly sample shape, appearance code, and pose, and each instances, even for the background, we can generate any kind of data that have the complex multiple object like this. One more thing is that comparing to the original NERF and pixel NERF and graph, they are whole learning in the color domain. In giraffe, they just use the picture generation, not a color generation. So because the color was just RGB, when a picture is going to the more high dimensional space, let's say 124 by 1. So we can easily expect it contains more information than the color value itself. Then we can generate the much better output. Yeah, this is the giraffe. So at testing time, we just sample, say, shape, appearance for each instance, and yeah, pose and viewpoint pose, background pose, and can generate output image. This is a giraffe. This is a detailed network over architecture. So this is pretty complicated. So yeah, if you are more interested in these details, please see the paper. Then I will briefly summarize the network. So comparing to the graph, we have to consider the large N kinds of the shape and appearance code. Shape and appearance code. Yeah, and yeah. Now with the networks, we generate the radius field. In this case, your feature field, not a color value, because this is a feature. Then in composition step, in composition operator, we just aggregated each feature vector in a common 3D space, but by considering this sigma as a weight parameter, we can just composite the feature vector. Then we can consider the volume rendering function, similar to the NERF. But in this case, because this is not a feature anymore, color anymore, this is just a feature, then we need an additional 2D generator, 2D decoder to decode this feature vector as a color value. So this is just FPN, like a 2D network, and we achieve the color value, and we use the discriminator to learn this whole network. This is a giraffe. And by using this, we can generate the controllable scenes. Interestingly, we can manipulate rotation, elevation, appearance, or depth, or the horizontal translation, because this is 3D aware generator. And one more thing is that because we in Giraffe we consider the multiple instance, we can generate the multi-object images like this in a 3D aware manner. So this is the Giraffe. Yeah, that's it. But yeah, Giraffe is just one example. There was so many kinds of extended version for this matrix. Yeah, that's it. So anyway, so Giraffe, the nerd can formulate any previous 3D computer vision problem in a impressive 3D aware manner. So yeah, there was so many kinds of paper, and in some presentation we will see few of them. Yeah, that's it. So this is the end of my lecture. Question so far. 자, 조금 빨리 왔는데 질문 여기까지. Question. No? Okay. Yeah, there is no more question. Let's move to the start presentation. So, yeah. 잠시만요. Here. Okay. So yeah, today we have a 5 presentation. So 5 presentation. So the first paper was the original by Jaewon. This is just a paper presentation. So by the way, so from today we will so each paper presentation is allowed to have the 10 minutes, and paper plus code will be the 20 minutes. Okay. 보상? Okay, I will let you know soon. 자, 이거 조금만 이거 보고 알려줄게요. 자, 재원 학생부터 가봅시다.
네, 교수님 화면 공유하겠습니다.
네.
네, 바로 시작하겠습니다.
네.
Hello, my name is Jaewon Lee. Let me introduce 2020 CCB oral paper named NERF, representing scenes as neural radiance fields for view synthesis. View synthesis aims to generate images of novel views from one or more given source views. With input images of several viewpoints, NERF learns the scene representation in order to render scenes from any viewpoint as below. The figure above shows the overall pipeline of the paper. To compute a 2D image seen from the position O towards direction D, they cast a ray for each pixel and sample points, denoted by RT, along the ray as shown in lower left. Here, Tn and Tf are the near and far bounds. Then they feed those points with its camera's direction into an MLP to produce a color and volume density, and composite those values into an image using volume rendering techniques, which I'll explain later specifically. The rendering function they use is differentiable, thus NERF can optimize the scene representation by minimizing the residual between synthesized and ground truth observed images. The paper represents a continuous scene as a 5D vector valued function whose input consists of 3D position x, y, z of a point on the ray and 2D viewing direction theta, phi of the camera, and whose output is an emitted color RGB and volume density sigma. In fact, going into the implementation level, they've expressed the viewing direction as a 3D Cartesian unit vector, which then the scene representation function should be a 6D vector value function. Anyways, they approximate this continuous scene representation with an MLP network. They encourage the representation to be multi-view consistent by restricting the network to predict the volume density sigma as a function of solely the location x, as you can see in the figure below, which is also called direction agnostic. On the other hand, they allow the RGB color to be predicted with the both location and viewing direction in order to get view-dependent RGB color, which is able to represent non-Lambertian effects. A Lambertian surface is a surface that appears uniformly bright from all directions of view. Then a non-Lambertian surface would mean the opposite, and most real-world objects have this property. Here are some examples of view-dependent RGB colors. As you can see, on the same location with different camera direction, the emitted radiance differs. Figure C shows the radiance distributions across the whole hemisphere of viewing direction. With the density and the emitted radiance of points on the ray, the expected color of the ray can be formulated as below by using principles from classical volume rendering. Function TT denotes the accumulated transmittance along the ray from Tn to T. In other words, it is the probability that the ray travels from Tn to T without any other bothering particle. Since MLP could only be queried at a fixed discrete set of points, the paper estimates its continuous integral using quadrature. They first sample endpoints through a stratified sampling approach where they partition the interval from Tn to Tf into n evenly spaced bins and then draw one sample uniformly at random from within each bin. Then they estimate the color CR with the quadrature rule as below. This function can be interpreted as the traditional alpha compositing, which is commonly used in graphics with alpha value as 1 minus exponential minus sigma delta. The paper proposed two techniques to improve optimizing NERF, which are the positional encoding and hierarchical volume sampling. They've empirically found that directly using the location and direction as the input to the network performs poorly at representing high frequency variation in color and geometry. Based on their observation and other recent works suggestions, they've added position encoding to map the inputs to a higher dimensional space before feeding to the MLP. Some people would have noticed similar mapping in transformer architecture, but the usage of transformer is different from NERF, where transformer uses it for providing discrete positions of tokens, as the input to the architecture does not contain any notion of order. Now to the hierarchical volume sampling. Simply rendering with the points using stratified sampling is inefficient since points with low volume density, such as points in free space and occluded regions, do not contribute to the rendered image. Therefore, instead of using a single network, they simultaneously optimize two networks, which are the coarse and fine network. They sample NC points in the same way as previously described and feed to the coarse network. Given the output of coarse output, they obtain a piecewise constant PDF along the ray with hat omega shown in the figure. After computing CDF, they conduct inverse transform sampling to sample NF additional point set. Finally, they compute the final rendered color with fine network at the union of the first and second set of samples, of which the number would be NC plus NF. The total loss is as follows in the right. Here are some qualitative results on real-world facing scenes. Here are the quantitative results in the ablation studies. As you can see, NERF outperforms prior works for view synthesis on synthetic datasets and real images. For the ablation studies, NERF shows remarkable improvement with the positional encoding, view dependence, and the hierarchical sampling. Thank you for listening to my presentation. Please feel free to ask any questions.
Okay, very thank you much. So, question. Yeah. So, most of the concepts are already discussed in the lecture. So, and Jaewon so discussed in detail. So, thank you. Other question? No? Okay, thank you very much. And let's move to the other paper. Okay, so next paper is learn visualization for optimizing coordinate-based neural representation. This is about the initialization for the neural network in NER. So this paper is by Jonghan. This is going to be the paper presentation. Jonghan.
혹시 화면 보이시나요?
네, 보입니다. So you have 10 minutes, okay?
Hello, my name is John. I'll be presenting on learn initializations for optimizing coordinate-based neural representations. Coordinate-based neural representations are optimized to map from an input coordinate x to the signal's value at that coordinate. A limitation is that computing network weights that produce a given signal typically requires solving an optimization problem by running many steps of gradient descent. And this can take hours depending on the problem. So common strategies to solve this issue is restricted to representing only signals within its learned Latin space, limiting its ability to express previous unseen target signals. This paper proposes learning the weight initializations for neural representations across a wide variety of underlying signal types, such as images, volumetric data, and 3D scenes. Compared to a standard random initialization using fixed learned values for initial network, weights act as a strong prior that enables both faster convergence during optimization and better generalization when only partial observations of the target signal is available. In the case of using neural representations for 3D reconstruction from images, learned initialization specialized to a particular shapenet class allows the network to recover 3D shape from a single image over the course of optimization, where a standard randomly initialized network fails unless provided with multiple input views. This paper setup applies an optimization-based meta-learned algorithm in order to produce initial weights better suited for representing that specific signal class. We define a finite signal T as a function mapping from a bounded set. A coordinate-based neural representation F theta for T is a fully connected neural network with D input and N output channels. If pointwise observation of the signal T is available, F theta can be supervised by gradient descent using L2 loss. Basic gradient descent applies the rules where theta, theta 0 denotes the initial network weights before any gradient steps are taken, and theta I denotes the weights after I steps of optimization. More sophisticated optimizers such as Atom keeps track of gradient descent moments over time to redirect the optimization trajectory. If T is a 3D object, MTP could be a 2D image captured of the object from a camera pose P, And recovering a neural representation for T from observations require solving an inverse problem by taking gradient steps on a loss that incorporates the forward model M. If M discards too much information about T, or the set of provided observations is too small, the resulting network may not match T closely. So the problem of trying to learn the initial weights of a network to serve as a good starting point for gradient descent across a distribution of tasks is addressed by optimization-based meta-learning algorithms such as mammal and reptile. In mammal, if we are given a task T, calculating the weights values requires taking M optimization steps, referred to as the inner loop. Mammal wraps an outer loop around the inner loop in order to learn the weights theta naught. In reptile, it uses the same setup as mammal, MAML, but applies a simpler update rule that does not require calculating second order gradients. And this rule moves previous weight initializations theta zero in the direction of task optimized weights. So if you look at the results, the meta learned initialization is specialized for the class of human face images. Standard initialization networks takes over 30 times as many iterations to reach the same quality as the two-step gradient steps from meta initialized networks. In the views synthesis experiments, they use a simplified NeRF model, simple NeRF, that maintains the same image supervision and volume rendering context. And unlike the original NeRF model, they do not feed in the viewing direction, and they use a single model instead of two coarse and fine models used by NeRF. The simple NeRF formulation relies on multi-view consistency for supervision, and therefore fails if naively applied to the task of single view reconstruction. However, if the model is trained starting from meta-learned initial weights, it is able to recover 3D geometry. The MV meta initialization has access to multiple views per object during meta learning, whereas the SV meta initialization only has access to a single view per object during meta learning. And all methods only receive a single input view during test time optimization. And here are the results for the single view shape net reconstruction. The phototourism dataset consists of thousands of post-tourist photographs of famous landmarks. The objective for this paper is to use these images to create an underlying representation that can be explored and rendered from a novel viewpoint and varying lighting conditions. The meta training datasets for each landmark consists of thousands of images with varying resolution and intrinsic extrinsic camera parameters. And at test time, they optimize the NeRF to reproduce the appearance of a new image and then render that simple NeRF from other viewpoints. So something like this. And that's the end of my presentation.
Okay, thank you very
For
much.
listening.
Okay, thank you. Question. Okay, so this paper, they used the memory to generate the long initialization for the NeRF. So it's a very, very interesting paper. So if you're interested in, please see in detail in the paper. Okay, thank you, Chonghwa. Yeah, let's move to the next paper. So next paper is pixel nerve neural lattice field from the one or few images, which is going to be paper was called by Martin. So please start.
So, hi, my name is Martin. I'm an exchange student from Germany at Korea University currently. And today you're going to hear more about the details of the pixel nerve neural radiance fields from one or few images introduced on CVPR 2021. So before we get into the more of the implementation details, I'd like to briefly touch upon the motivation of extending NERF and the way that Pixel NERF did, because although NERF blasted many of its competitive papers in terms of novel view synthesis, it still had a few shortcomings that Pixel NERF actively tries to tackle. In this context, NERF still required many calibrated views, which we can see in the picture to the left over here, that they required many pictures that were like difficult to take, and this is infeasible in most real world context and resulted in high costs of even doing. So there would be and there always will be also limited data for training on this type. Also, it is still limited to single object scenes, such as this drum set over here, or the Lego tractor we saw, or anything else, and cannot really synthesize real world scenes as we have them around us. The third point is that even though there is like some training going on in NERF, it only trains to a specific scene, and it's not able to share the knowledge between scenes, and it does not learn any scene priors. So this is probably a bit of a waste of computation and anything else. So there is optimization potential in the NERF concept. This is where Pixel NERF basically comes in. They tackle the first point of requiring so many calibrated views by a few shot approach, and can in fact synthesize a three-dimensional view, or like so one of those radiant fields, by as little as one image. Also, they use spatial image features, or they extract these features from the images. So they can learn scene priors by that, which means that by using those images and later training the network, they can actually share knowledge between those images, which will result in shorter computation times and all these things. Taking a look at the architecture, at least I first drawn this up in comparison to NERF again, because looking at it maybe from like the first view, it does look very similar. That's why on the right side we can see it has basically the same rendering techniques and the same loss functions as NERF had. And what also looks similar is the actual neural radiance or the neural network that represents the radiance field. The obvious difference that we can see in the architecture is that starting from the input, we do not input as many different pictures as we had in NERF, but the specific case we show here, we've already had it in the lecture. It's basically the pixel NERF architecture for a single image as an input. And as we can see, the image is not input directly into the network, but there is like a convolutional neural network which works as an encoder before. This is usually, or at least in the implementation they had, this is a ResNet35 using 5 blocks, and it is used to extract a feature pyramid of features which are then later used further on. So these similar to how it was in NERF again, these features are then input into the next network, along with the query points and the array basically. So yeah, this so as it may look like, the main difference between NERF and pixel NERF is that we have this convolutional neural network right here extracting the features. However, since pixel NERF is also able to synthesize views from multiple pictures, there's also a lot different in this part of the network, which we're going to look at in the next slide. So yes, this is basically what we see here. It's basically a detailed drawing of what of this network, and it surmounts to different kinds of residual blocks. What Pixel NERF has actually done, it has a two-step approach, we can say, in terms of the neural radiance field, which is shown here. We have like the F1 part and the F2 part. For the F1 part, we basically have a neural network representing the radiance field for each of the input images, and for the second part, we then combine these radiance fields in a single radiance field and output the RGB and sigma value after rendering. However, it's not as this is not as simple as it actually seems. There's a few other differences going on under the hood. So if you look at the inputs of the images, or of the inputs of the features that we input into the network, we do not we put them. Those features are aligned to each pixel, and these pixels are actually transformed and projected into the space of each image, so that since each image obviously has its own coordinate space, these points are transformed and projected before. The same goes for the actual query. In terms of the points and the camera view, Pixel NERF uses the same positional encoding that was introduced in NERF. This was the high dimensional encoding, which was introduced earlier in the lecture. And again, for each picture, the query points and the camera view is transformed into the coordinate system of the image, which means that we have these residual blocks for each image. These blocks are repeated 3 times after each other, and then we have an average pooling operation, which combines all of that and our final residual blocks, which results in our final feature, or not features, but then in the final RGB values that we have. One additional detail I can mention is that although these are linear layers are depicted in the that these green bars are depicted as linear layers in the paper and in this picture, the actual implementation on GitHub often use a residual block again instead of so basically a residual block inside of these linear layers. But we're going to get to that once we're into the code review part. So since the actual rendering part and the loss function is the same as NERF, I'm not going to touch upon that a lot or even at all. Let's just take a look at some of the results instead. We've had most of this in the lecture before, but the astounding part of the results is actually that on the top left part, as we see here, this is actually this is a view that was fed with only 3 images. So to the left, we have those 3 images, and they are once fed to Pixel NERF on the top and to NERF on the bottom. And we can see that from these pictures, the Pixel NERF is able to create a view that is not perfectly photorealistic, but actually understandable and surprisingly nice. NERF, however, just creates some sort of a static fuzzy picture, and we cannot even comprehend a scene or anything. So in terms of the few shot approach, Pixel NERF has definitely done a good job in realizing that. In terms of not multi-object scenes, but like in terms of just representing single scenes in a few shot setting, Pixel pixel nerf also shows basically the best results, as we can see when compared to the different methods that we have. The ground truth obviously shows up a bit better, but for the other cases, the other compared methods have more shortcomings than pixel nerf does. And what we see on the bottom here, again, is basically the table of is basically the different benchmarks for these objects. There are a few more objects, but what we can see is that pixel nerf basically outperforms for every object, outperforms every different kind of method in most of the benchmarks. So yeah. That was my presentation. If you have questions about the presentation or the architecture, feel free to ask now. If not, I would hop into the code review. All right, I take that as a no. So starting from with the code review, the main entrance point to our to the pixel nerf module is the so-called.
By the way, Martin, please upload your GitHub site on our Google Sheet.
Oh yes, I will do so. I will do so. My apologies. So yes, the main entrance module for pixel nerf is the so-called pixel nerf RFNet. This is essentially, when we remember our architecture, the very left part where we input our feature. The initialization allows for a lot of different settings, such as using different encoders. I mentioned earlier that the encoder is a ResNet34 most of the time, but in the implementation that the authors uploaded, they also give the possibility of using a standard or very simple convolutional neural network. And there's a lot of other options that can be changed as well in regards to nerf, such as if we want to use the positional encodings that were introduced, or we want to go without them. And this is most of the things that are set in the initialization part of the pixel nerfnet module. So the first function that we then have is the encode function. This basically takes care of encoding all the image and then extracting our feature pyramid from that. The actual call to the encoder is done at this point. As I said, the encoder can either be a ResNet34 or like a specific other convolutional that can be used, although the authors stress the fact that only the ResNet34 is properly tested. Since the ResNet34 is should be, or the ResNet in general should be known to us, I will not hop into that part of the code. So after extracting all the features, what happens here basically is that there's we do some more transformations based on the focal points of the camera and these kind of things. And yes, and in case we want to do this, the code actually uses a second global encoder to encode additional global features. So much to the encoding. This is the actual forward pass that happens with the inside of the network. So as mentioned earlier, we transform the query points into the camera spaces of the input views. We do not use a canonical view as was the case in the NERV paper. So each point of the query for each image is transformed into the specific view here. And at this point, these coordinates are additionally encoded. The same is done with the not only the coordinates, but also the view directions in here. And then the positional encodings are applied. I will not go into the positional encodings again because it's actually part of the NERV paper, and the technology that's used is identical. So the interesting part is actually that, where am I? Exactly. The interesting part is that the encoder is actually frozen for most parts of the training, so that that they're or for large parts of the forward pass as well. And after that point, we start we start with some additional transformations before we actually go into the nerve part. Now, the nerve is again implemented as in the original nerve paper with a coarse and a fine network. Interestingly, in this implementation that the authors uploaded to GitHub, the networks are actually the same for the coarse and the fine network. This is customizable in the configuration, but for some reason the configuration shows exactly the same values for each of those networks. But since there's like a lot of difference to the nerve to the network of the nerve paper, we will take a look at the network now here. Also in this one, as I've mentioned before, we can hop back to the presentation so I can show this real quick. These so-called linear layers, they can either be really implemented as linear layers or as resonets again. And the function over here, make MLP, reflects this. They either have like have the linear layers again portrayed as residual blocks, or have them as linear layers. For the sake of this code review, I'm going to take the simple linear layers with this one, which is how it was presented in the paper as well. So this is the so-called implicit net, and this is basically the implementation of this part of the pixel nerve for orientation purposes. So again, we have several initialization methods. The number of residual blocks that we have are customizable, and the number of actual layers we have in between the residual blocks are customizable, and the actual layers are initialized with initial weights in the initialization part here. In the forward pass, basically we go through each layer of each residual block that we have, and basically pass the features through. So yeah, this is the first one. This is basically the first layer we're going through, and it is the layer up here where we first get our features for the first time. And yeah, those are combined in a residual block that we've had, and then passed on through multiple linear layers again in here basically. So yeah, after and here exactly, well, this was kind of inaccurate what I've just said. This is only the residual block. If we have a residual block right now, if it's a standard linear layer as in the architecture, then it will just apply the linear layer with its activation functions afterwards. And once all layers have run through of the residual blocks, then the value will be returned out. So yeah, that was the MLP model, or the that was basically the part of the nerf that we've had. After, let me get back to the forward pass in here. Exactly, here we were. So again, the coarse and fine networks are applied, even though in this implementation they basically perform the same network things. After that, we again do some reshaping before basically applying the final layers and the sigmoid, and then returning the output. The actual rendering is done in a different module, but since it's identical to the NERV paper, again, I did not really brush upon that as well. So yeah, this was my code review, and I think time's up so far. But if you guys have any questions, feel free to ask.
Right. Thank you very much. Any question for this paper? No? Okay, thank you again, Martin. And yeah, what time? Yeah, we have 2 more papers. Okay, let's take a 3-minute break because we have 2 more papers. So let's take a 3-minute break and let me start 4 p.m. 우리 10분만 쉬었다가 이제 민서 학생부터 4시에 다시 시작합시다. Okay, so yeah, let's go back. Right, so we are discussing the NERV, right? So okay, so let's discuss one more paper, MIP NERV, a multi-scale implementation for the anti-aliasing neural radiance field. This is just a paper presentation by Minso. Please, please start. 혹시 민서 선생님 돌아왔나요? 왔구나. 네.
네네. 혹시 화면 보이시나요?
네, 보입니다.
Okay. So let's start the presentation. I'm Min-seok Ju in Machine Learning and Vision Lab. Today, I'm here to present MIP-NERV, a multi-scale representation for anti-aliasing neural radiance fields. This paper was accepted to ICCV 2021 oral. This is the contents of this presentation. I will skip the basic nerve explanation and focus on the methods proposed in MIMNERV. First of all, as you all know, NERF showed very good quality for view synthesis by learning 3D objects and scenes through neural radiance field. But there is a problem in NERF. NERF's method works well when training set and test set are observed at a constant distance like this. But when the training images observe scene content at multiple resolution, rendering from the recovered nerve appear blurred in close-up views and contain aliasing artifacts in distance views like this. These are called JGs and are one of the most common problems when sampling images. You can see the results in 1/8 resolution are bad. Learning nerve from images from multi-scale also does not improve the situation. So let's briefly go over aliasing and min mapping, which are mainly covered in this paper. Aliasing occurs when your sampling rate is not high enough to capture the amount of detail in your images. This can give you the wrong image like this. This region is high frequency, but our sampling interval or sampling rate is very low, so the image is broken. There are two main ways to solve this problem in computer vision. These are supersampling and pre-filtering methods. Supersampling is a sampling more than the Nyquist rate. This is an effective strategy to reduce aliasing, but it is expensive. It is not suitable for the NERV method, which already performs a lot of MFP operations per ray. Next, pre-filtering based techniques use a low-pass filter like filter to decrease the Nyquist frequency. So you can calculate the filter in advance, apply it, and downsample repeatedly to obtain a normal image. This is called a Gaussian pyramid. Similarly, a method of effectively rendering without aliasing in computer graphics is called min mapping. In the figure, you can see the texture mapping using a min map. So inspired by this, authors proposed the MIMNERV. This figure is a simple pipeline. NERV infers RGB of a pixel by sampling point through one ray per pixel, but MIMNERV renders using a conical frustum. Here, it is important to use a Gaussian region, not the point, so that the network can infer the scale. These conical frustums are the featurized with integrated positional encoding, IPE, which works by approximating the frustum with multivariate Gaussian. In fact, it is very difficult to explain, but the main paper and appendix describe in detail how to approximate it and calculate it. This figure in the paper is very helpful for understanding. The method is well presented. Look at the figure in positional encoding in NERV. At this interval, since the interval is narrow, there is no big problem with the method of NERV. But over a wide interval, we have to do a lot of sampling, but aliasing occurs because NERV encodes all frequency equally. In NERV, the parameter L of the positional encoding is fixed, so this cannot serve at the interval of this barrier scale. However, in the case of IPE in MIMNERV, by integrating P features over each interval, the high frequency dimensions of features shrink toward zero, like this, when the period of the frequency is small compared to size of the interval. It's very high frequency, but its interval is too large. This is very similar to min mapping with smooth high frequency component when sampling at low resolution. IPE can be viewed as a generic version of PE. This process is well illustrated in this clip. IPE generates positional encoding features by understanding large and small volumes through the multivariate Gaussian. In NERV encodes all features equally, but IPE preserves or softly removes frequency according to the interval. This is the main content of the MIMNERV. Next is optimization problem. Mid-nerve behave similar to nerve except for IPE or contrasting. However, here we can see one more advantages of mid-nerve. Nerve uses hierarchical sampling with two distinct MRP, coarse network and fine network. But mid-nerve scale-aware structure allow us to merge these separate MRP. So mid-nerve use a single MRP with a parameter setup like this. This has many advantages in terms of efficiency. This table shows a quantitative results of nerve and mid-nerve. It can be seen that the performance of mid-nerve is better than of nerve under the same condition. And it also shows the effectiveness of IPE method in ablation study. The left shows the result when tracing only with a single scale data set. Despite the favorable setting for nerve, mid-nerve showed better results. The table on the right shows the result of applying supersampling to the nerve. It shows that it takes a lot of time. Here, the results of the mid-nerve are slightly better. Finally, qualitative results. At the version of resolution, various resolution, a mid-nerve demonstrates a constant good performance about SSIM. Yes, it's a very interesting video. You can see that mid-nerve works well with a multi-scale resolution. Let's play the video again. Yes, in the case of images rendered from a distance, aliasing occurs. But in mid-nerve, this problem has been solved. So, and it produces very clear images than nerve. In conclusion, concasting and IP feature enable an MRP to run a multi-scale representation of scene. This model reduces error rates relative to nerve by 60% on multi-scale data set and 70% on nerve on single scale data set, and is 7% faster than nerve. But in the paper, the authors did not experiment on the real world data set like RRFF, and the region is in supplementary. This was covered by mid-nerve 360 that was accepted to CBPR this year. So refer to this paper. This is the end of my presentation. Thank you for listening.
Right, thank you very much. Question. By the way, mid-nerve is very interesting paper, and compared to the original nerve, the mid-nerve is going to be the good baseline for your nerve variance. So yeah, if you're interested, please see even code in the product side. Okay, so no more question. Right, thank you very much. And let's move to the final presentation. Okay, so yeah, final presentation. Title of the final presentation is Neural Sparse voxel field, which is going to be paper first code by Min-seop. Yeah, please start.
Okay, so hello everyone. My name is Min-seop Kwak.
스크린이 뒤로 되어 있는 것 같은데 잘못되어 있는 것 같은데. 네.
아 그렇군요. 그렇군요. 죄송합니다. 잠시만요. 거꾸로 됐구나. 이제 맞나요? 네, 이제.
네, 잘 나옵니다. 네.
네, 이제 맞는 것 같네요. Okay, so hello everyone. My name is Min-seop Kwak in Professor SeungryongKim's Siegel Lab Computer Vision Laboratory, and I'm here to present mainly neurosparse voxel fields, 2020 NEUROS paper, with a small connection to a very recent paper by NVIDIA called Instant NGP. So I'll go straight into the topic. So to briefly go over all the NERF related stuff that we just saw, NERF can be summarized into three main contributions. It's mainly a 5D radiance field encoded into a 8-layer MLP, a very simple structure. But simply inputting the three-dimensional coordinates into the network causes something called spectral bias, which means the network only tries to optimize using the least amount of dimensions possible. So it results very low dimensional, very low frequency imagery. As a result, these people use positional encoding, also named Fourier encoding, to boost the dimension of the input into 6D dimension and put it into the network. Also, it comes with another stratified sampling strategy regarding coarse and fine networks for efficient sampling. And this has shown amazing 3D reconstruction and novel view synthesis performances. However, NERF is not without weaknesses. It has three main weaknesses that neurosparse voxel field tries to tackle. So first, sampling scheme. Due to the volume rendering strategy, NERF must sample and evaluate even the empty spaces. So even when the space seems to be very clear and is bound to be is so obviously empty, it has to sample it and push it through the network. And that leads to the second problem, which is the optimization time. The weaknesses in number one means the optimization process leaves room for further better algorithm. So which means it contributes to extremely long optimization time, which is like 1 to 2 days required by NERF to optimize to a single scene, which is obscenely long and impractical for real life applications. The third one is controllability. So original NERF only reconstructs the given scene and does not allow the user to control the scene or edit it in a meaningful way. So improving this is also a NERF's main NERF's main room for improvement. So all of these weaknesses come from the inherent nature of implicit representations. Explicit representations such as mesh or voxels do not share this weakness, which is why it has been so widely used in graphics community thus far. So you can think of an interesting idea. How about combining these two? How about combining the implicit and explicit representation into one efficient representation? And that is neurosparse voxel fields. So original NERF can be described as an image above. So it samples every single point uniformly in an array, and regardless of where they're from, they're equally parallelly put into an MLP that encodes both spatial information and rendering information. However, neurosparse voxel field separates this into two different representations. So first they use voxels, and these are not ordinary voxels, but sparse voxels, which means they are existing in some places and non-existent in others. How it comes to be, I will explain later. But so what this network does is it only samples the points that are within the voxels. If so, where it goes, you can simply mathematically compute whether the ray intersects the voxels or not. And if it doesn't intersect it, you can just ignore the points, right? But if it does intersect it, they go into the voxel and see what kind of information has been encoded in the voxel. This encoded information is used to put into an MLP, which functions as a renderer, and this results color and density output just like original NERF. So this, in a way, is a reinterpretation of NERF architecture. So the visualization and overall pipeline of NERF is like this. You see the sparse voxel up there, which is something I'll explain later, but you can see that it's not a square voxel like a traditional voxel, but somehow it's where the object is and where the object is not. So it gives you meaningful information about the occupancy explicit way. And it goes to something called evaluation within intersecting voxels and accumulating these values in an alpha compositing way, just like an original NeRF results a predicted image. And the results, all the results that come out, the color novel view synthesis, the depth map, and the voxels are depicted in the GIF image that comes below. So let's get into details. Voxel representation. So what they do is as I said, they only sample points within the voxels. And these are called voxel bounded implicit fields, but because the feature for the point does not come from a network, but it comes from the vertices of voxels. So a voxel is a cube, so it has 8 vertices, right? And they use trilinear interpolation to find the mean value of all the features that have been encoded into the 8 vertices. And they are optimized along with the network. So as the network is optimized, each features encoded in each vertices is also optimized at the same time. And this is direct optimization. There's no network that comes between the vertices and the original and the feature that comes in the voxel. So what they, as it says in the paper right here, they do trilinear interpolation represented by X, and then they go through the positional encoding, and then this value, that finished positional encoding, GIP, is what goes into the final MLP network. So yeah, so this is the architecture. These are the voxel embeddings. There are 8 of them. And then they do trilinear interpolation right here. And then they go through positional encoding. And then they go through these MLP layers, just like in NeRF. But you can see that the network is way smaller now. The MLP network is way smaller because it only has to encode the rendering information. And this is where the directional information comes in. So directional information comes in, color is rendered, density is rendered, and everything from here is the same as NeRF. Now you may wonder how these voxels become this well-defined kind of 3D explicit representation. And it's actually quite simple. So what they do is they start with this huge, large voxel that we all know of. So that's not sparse. But what they do is they randomly and uniformly sample 16 to 16 cubes. So this is right here, 16 times 16 times 16 points within each voxel. And by doing that, they can see whether this voxel has density or not. So if all the points in the voxel has 0 density, then they can just prune this voxel, right? They can just say, okay, so this voxel has nothing. Let's just move on, and they can eliminate this voxel. If the voxel has a certain value of densities over a threshold, then they can see, okay, let's look closer at this voxel. So they split this voxel into 8 different voxels. So yeah, so it's quite intuitive, right? So a voxel divided half is 8 voxels, and that's how it goes down. It continues to do this after a certain amount of steps so that the voxel becomes more and more well-defined and more explicit and becomes more efficient, gives efficient information for novel view synthesis. And what they also do is early termination. So when the ray is passing by, when they're doing ray marching and the value is above a certain, when the value of density reaches a certain step, they just and the points after this point are no longer queried. So by using all of these techniques, they manage to do solve a lot of NeRF problems. And by the way, this is the loss. That's basically the same as NeRF, except for this small regularization term. And so let's go into the results. They managed to boost the speed of network, and like this. So this is original NeRF, and they managed to, I think, reduce the speed of by pruning away all the unimportant locations and by using early stopping by about 10 times. So this neural sparse voxel fields is 10 times faster than NeRF. Also, it enables a limited amount of editability because you can just take the voxels and put it anywhere and have images rendered, right? So this is what they do. They first have all these voxels optimized, sparse voxels, and they put them together. And when they render array through it, they can have these kind of images where all the Blender optimized NeRF scenes are just compiled into one. And there's this final experiment, which is quite interesting. So up until now, the voxel and MLP were trained together, right? But we can imagine, like, since they're separate, what if we just switch the images? Or if even better, what if we just have only the voxels change and have a trained MLP shared all the networks? So there's only one MLP that takes care of all the scenes and all the voxel representations. And what will happen? And the result is it does really well. So they use a hypernetwork to simulate a similar setting in NeRF, and they say that this voxel representation is the best way to have a shared renderer and a separate geometry that can output this kind of results. And we can also reinterpret this in a very interesting way. So we can say that this voxel has graphic text, the geometrical content, and this MLP has style, right? What if we change the style? What if we can manipulate the style of the network by changing the MLP? And this is exactly what a paper in NeurIPS 2021 called IVR, Multi-View Neural Service Reconstruction by Disentangling Geometry Appearance. This paper does. So they have geometry and they have trend renderer, and they switch the renderer and find that textures and the colors of the of the geometry of the render images can be switched like this, which is very interesting and has a lot of implications. I also prepared another paper called Enston NGP that's related to this, but I think I'm out of time, so I'll go straight into code explanation. Okay, so this is pseudocode that is in the supplementary material, and I'll just go along matching actual code. And also, I find that nobody else has done the overview of NeRF code itself. So I think I'll be going over that as well, as it's also a part of the neurosparse voxel field. So the input are like this, and then they initialize transparency and color and depth like this, and they find the ray voxel intersections. So the main problem that comes is they also have to care about the voxel intersections as well as the sample points. And they do it by sorting. So they mathematically calculate all the existing voxels and intersecting rays, and they just use Python sort. So the closest one comes to the front, and the furthest one comes to last. And they have this kind of nice ordered representation where they can actually sample points. So between all these intervals, they obtain midpoints, and then they sample it in the condition that the accumulation is actually bigger than threshold. So if the accumulation is smaller than threshold, you can see that it has come to early stopping and they will no longer count. But if it's not, then they will continue to put them through the MLP and render them. And in the end, it comes like this. So this is for the depth representation, and this is the color representation. By this, you can see that you can render depth just in the same way you can render a color map, and you get these color map and depth map and accumulation map as a output. So this is main training loop of NeRF. So very simple. All you have to look at here is train p step, which is right here. I only brought the code snippets, so it might be difficult for you to look, but I'll upload the GitHub as well. So if anyone wants to take a closer look, you can go and see. So this is optimization step where they calculate loss. And this model is the MLP point. So this is where the point is passed through, and this is the results. All the results come out here, and RGB displacement and accumulation comes out. And this RGB value is basically the image, right? So dispatch pixels is actually the original GT image, and they use MSE loss squared and then mean in order to calculate the loss, and this loss gets put back here, and then they're optimized. So let's take a closer look at the main section of our model, which is just a simple MLP with volume measuring. So first, the most important part is the sampling part, right? So they have to sample the points along the rays, and how it comes by is they have these p-values in the lin space. So this is maybe I'm going too specific, but this you have number of samples, and you know that this is a NumPy way of forming a uniform interval, and they transform this interval into z values, which comes between 1 and 0, 0 and 1. And because they have randomized the sampling process, they sample points between these intervals. They sample points between the intervals, and then between these intervals, they have the midpoints. So the midpoints is basically the midpoint of the interval. So it stands for this midpoint is basically what goes into the network. This midpoint basically represents the interval, and these values are all summed up and sorted out, and they are put out. So they are put out in set values and samples. These samples actually mean the 3D coordinates, and these z values mean which value they have on the linear line that represents array. And these values, these sample coordinate values, they go into this part, positional encoding, which has been also mentioned in previous papers. Basically, they have these options for minimal degree and the maximum degree to which the frequency will be represented. And the default setting is minimum degree 1 and maximum degree 10. So they use this code right here to calculate all the scales, different frequencies, and they just multiply them to the network, to the given input value, positional encoding. And the result of this is the positional encoding that we saw that has been geometrically transformed. And this is also called the Fourier feature. So that's why they see here Fourier feature. And in the end, they also need the original coordinate, XYZ coordinate, along with the Fourier feature. So they concatenate these two features, which results 63-digit dimension feature. And this is what is output. So this is called samples encoding. And the samples encoding finally goes into the MLP network, MLP structure, which is very simple. So I'll not go into the, and volumetric rendering. So this is the part where the volumetric rendering occurs. Unlike what they say in original NERF paper, you can see that everything happens in parallel. So they say it's ray marching, but because every point is sampled uniformly and does not require the previous step in order to calculate the next ray marching step, they all come out at once, and they can just accumulate the entire product to calculate the transmittance. And this is the part, this is the weight the professor talked about. This is transmittance weight. And by multiplying this to the RGB values and accumulate right here, sum, it can have the final RGB value that comes out. And this, by combining all the rays, you can have a rendered image in the end. And this is basically like a code form of the equation that is in the left corner, left bottom corner, that stands for the color value that comes out in the end. And I'm out of time, so I'll explain this part shortly. So this is how they calculate the ray voxel intersections. You can see it has nothing to do with deep learning. It's geometrical and mathematical, and they mask out the points that do not intersect. And that's how they filter out all the points that do not go into the voxels. And this part is the trilinear interpolation, where they have these point features, and they are going through the trilinear interpolation right here, after which they'll go through the positional encoding for final small layer render MLP input. Yeah, so this is basically all of the pseudocode explained, including the NERF section as well. And thank you for listening to my thank you for listening to my presentation. If anyone has any questions, please feel free to ask.
Right, thank you very much. Question. So yeah, it was very interesting paper. So this paper was first attempt to, it's not first attempt, it tried to combine the advantage of the explicit representation and implicit representation. So it's a very interesting paper. Any question in this paper? No? Okay, thank you, Minsa. Okay, so thank you very much. 네. Okay, thank you very much. And so from last week, we discussed the 3D computer vision, right? So we discussed so many papers, so please review. So review the main papers, right? And one more thing is that we will have a final exam, right? So after 2 weeks, so please prepare. Maybe next week will be the last lecture, right? So I will let you know last lecture's the topic soon. Yeah. Any question? No? Right. So that's it. So this is end of this lecture, and this is end of 3D computer part. By the way, there will be the quiz about the task correspondence and the 3D computer vision, maybe which will be distributed today. So please stay tuned. And more question, right? Okay, so that's it. So this is end of today's lecture, and this is end of 3D computer vision part. And thank you very much, and see you next week. 여러분 아까 공지했던 것처럼 이제 이번 주까지 해서 3D 컴퓨터 비전 파트 끝났고요. 우리 다음 주 마지막 시간 보고 이제 2주 후에 기말고사 시간에 보도록 합시다. 고생 많으셨고요. 우리 다음 주에 봅시다.